we first do a basic general detection of spheres from these point clouds. So we remove the whole point, similar to what we talked about with cylinders, similar to what you're going to be doing in your second assignment for your plane. We are now detecting automatically only those points that follow a spherical pattern. Once we do that, we basically remove that, and we end up with something nice like this. Then the second part here is to actually go and identify, because we do not know what the location of each and every one of these, let's say, nodes are. Now we have to go and process this, right? So we have to go and identify it backwards and bring it to this simple part so that we can know where those deltas are. We can see if this design was actually more efficient than the design that we are actually having right now. Because if we are making some comparison, it's good to make the comparison with the original version, right? So for this, we go and bring it back. These are curved wooden surfaces, yeah? But now we have changed through dimensionality reduction by knowing how this design is done from a linear curve detection from point clouds in 3 dimensions, okay? We've actually reduced that problem to a line detection from 2D points. But how do we get from here to here? Okay, you have to extract linear features. So one benefit of actually bringing into 2 dimensions is that you can actually utilize some image processing methodologies as well. In this case, I use direct point cloud processing because it was simple to perform that. I basically use my circle fitting algorithm to extract the outer area. This by itself would only leave us with a bunch of lines. After that, I would have to identify for every point a neighborhood around that point. Why do I have to do that? Because I need to know the pattern of what that particular set of points are going to follow. So the first thing is, well, what size of neighborhood do we even pick? I want to say whether I imagine we have a bunch of points about all of these tables here. They're all planar points, right? There are 2 issues that exist in point clouds. One is that you have some random measurement errors. That's one side, okay? Assuming that we don't even have that, we need to find for every point a set of points around it. How do we even do that? Do we get 1 centimeter out, 5 centimeters out, 10 centimeters out? To what level? That depends on your noise level. That depends on the resolution of your point cloud. All of these factors need to be taken under consideration. So I put together a process where you can actually set it up as an optimization problem that works very, very well for linear and planar, basically, or anything that has a hyperplane associated with it or can be actually identified based on that. And I use Bayesian optimization to basically get that information. What I get at the end is basically these nice neighborhood sizes, where here I would get smaller neighborhoods, and then here I get larger neighborhoods. Now, what is the benefit of getting larger neighborhoods in those linear elements? If I get a very, very small neighborhood there, let's say I get a very, very small neighborhood here instead of getting a large neighborhood, that particular linear object would start looking more like a plane. So imagine this. You have a square, AA, right? This is a plane, right? Now imagine you have this and something like this, yeah? And you have, let's say, 6 A's this way. This looks more like a line, right? Yeah? So that's what that difference is. If this would have been a small neighborhood size, okay, this would have looked more like this, and it would have identified it as a plane, right? Or in this case, as a square, not a line, right? If this is larger, because nothing else is around it, right, it would identify it properly. So we expect the optimization or the optimal neighborhood here to have larger neighborhood sizes so that it could identify more points around it. And here, where if you get more points or less points, it doesn't really matter, right? If you get more points, it just becomes a bit more confused, right? To get smaller neighborhood points. Then you have to perform what we call a principal component analysis. This is literally what we did for your plane detection or hyperplane fitting that we did, right? We said we do a principal component analysis, which is the eigenvalue decomposition of the covariance matrix, right? And we go, if we want to find the, let's say, plane, we get the eigenvector corresponding to the smallest eigenvalue. That would be the direction of the surface normal. For a line, we said that that is going to be synonymous to finding the largest eigenvalue, right? And direction of that, that would be the direction of the line. And the direction orthogonal to that, that would represent the smallest amount of eigenvalue, right? So that's what the principal component provides us. So then if I look at the principal component, whether I do the orthogonal or the other way around, this would just be changing 90 degrees because it's plane, right? So one is going to be in the direction of the line, the other one is going to be orthogonal, right? These are the two principal components. If I do the eigenvalue decomposition, knowing the good neighborhood, if I don't use the small neighborhood, because if I use the small neighborhood, well, it might actually confuse whether it's this direction or this direction. Imagine if it cuts a bit less here, then definitely this direction would be the maximum eigenvalue, right? If I do it that way, then I would basically identify the peaks of where the direction of these lines are actually following, because we know that this is going to be a deltoid and very, very regular. Then we can get peaks in each and every one of these. You are going to do something similar for your plane detection using point clouds, because you're going to be using histogram of point heights. Once you get the histogram of the point heights of the point cloud that I provided, because it's level and the floors are level, the majority of the points would actually follow certain patterns. You don't necessarily need to do a principal component analysis to get that information, but from here on, it's going to be a similar process. In this case, you get some peaks. What does this mean? If I look at the peak here, okay, in the first one that is close to 0 degrees, that basically represents this one. I go and rotate it all the way. This is what it looks like. Actually, this here, I rotate it all the way. This one represents this one here. I go and I rotate that all the way. I get a bunch of lines that are orthogonal. I find this one here, which represents this one, which represents this one here, you see? And I go and I rotate it that way. So that location goes orthogonal. You can do it this way as well. It doesn't matter. As long as it's consistent, you can use the same algorithm to identify what is going to be the majority direction of your points, okay? So you get the majority direction. Now, once this is basically identified like this, you have a bunch of peaks on these directions too. Once you identify these peaks, that would be the locations of your lines for each and every one of these peaks of the orientation. There's always some level of overfitting or underfitting, right? So because of that, you are going to be getting some of these maximas or minimas that are going to be prominent and some of them that are not. So all of the green ones are the maximas that we want. And there's some here that we really don't want, right? They're green, but they're just, they're not prominent. But they would be identified as a peak. That means that if I want to select all of these peaks, I would have a bunch of these that are not correct. How do I weed them out and get this, which are all of the ones that are acceptable? And some of the ones that you see, like this one here, like this one here, like this one here, are notified in our peak detection, but are not prominent. They're a bit wider, right? But that is very data specific. That is very application specific. How do you do that? Well, I said, okay, in order to do that, we need to simulate a bunch of these. Once you simulate it, what do we get? We get a bunch of data, and then from those data points, we can actually train a machine learning model to be able to give us what would be the acceptable norms based on our simulated data. And this simulated data is millions of data, different thicknesses, different noise levels, different sizes, different widths, everything, okay? So we have to be creative about it to be able to find out what this is. And in this case, I've used a support vector machine classifier, which what it really does is goes and it tries to find by means of some transformation, what would be the set of points that would separate these two classes? So I have a bunch of, let's say, lines, or a bunch of, let's say, modes in this case, that would be constituted as prominent and correct, and a bunch of them that are not. How do I know that? Because I know this data, I know which one of these modes that could have been identified are correct. And I use my same mode detection algorithm to see which ones are identified as incorrect, and then find the properties of those that are incorrect, and then go and train it based on selecting the ones that are correct. So these are some of the results. So for instance, for 3 different types, once we basically do the dimensionality reduction and create it into the grids, we were able to identify each and every one of these lines. If I use a k-means algorithm using the exact same processes, exact same principal component analysis, exact same neighborhood definition, we get worse results. And then, for instance, for spectral clustering, we get some other results that are worse. These are obviously unsupervised methods, but if we don't have the data, we have to use unsupervised methods. So this is the final results. We get a bunch of these, and then we go and project it back to that surface that we had, and then we get the nodes, and then from the nodes, we can always get the elements as well. And then from that, we can now start processing it however way we want, right? So we're preparing it for the second part of our analysis. And this is, for instance, the result of these. Make sense? All of these are utilizing the exact same procedure and the exact same methodology.